applications, only to find your robot drifting, your drone's attitude accuracy decreasing, or your navigation system becoming unstable. In fact, many sports control and navigation project failures often stem not from bad algorithms, but from choosing the wrong IMU. Today, we'll explain each key IMU parameter in a practical, easy-to-understand way. After watching this video, you will know exactly how to select the right IMU for your application, whether you are developing robots, drones, autonomous vehicles, marine systems, or precision navigation equipment. Let's get started. Chapter 1. What is an IMU? Before diving into the specifications, let's first understand what an IMU actually is. A standard IMU consists of a 3-axis gyroscope, a 3-axis accelerometer. Combining these two creates a 6-axis IMU. If a 3-axis magnetometer is added, it becomes a 9-axis IMU, commonly referred to as an AHRS. Each sensor performs a specific function. The gyroscope measures angular velocity and detects rotational motion. The accelerometer measures acceleration and gravity, helping to determine the tilt angle. The magnetometer provides heading information relative to magnetic north. Many beginners assume that a 9-axis IMU is always superior to a 6-axis IMU. This is not the case. In environments with strong magnetic interference, such as factories, vehicle interiors, or areas near motors, a magnetometer can actually introduce errors rather than improve performance. Therefore, the first step in selecting an IMU is to understand your application environment. Chapter 2. Detailed explanation of gyroscope parameters. The gyroscope is typically the most critical component within an IMU, as it directly impacts attitude accuracy and navigation performance. Let us begin with the angular rate range. Common ranges include 250 degrees per second, 500 degrees per second, 1000 degrees per second, 2000 degrees per second. Many people assume that a wider range is better. In reality, this is not the case. A wider range usually implies lower resolution and higher noise. For low-speed applications such as camera stabilization systems or static monitoring, a smaller measurement range often yields cleaner results. In contrast, racing drones, missile guidance systems, and high-speed robots require a larger measurement range. Please select the smallest measurement range capable of covering the maximum range of motion you anticipate. Next is one of the most critical parameters, bias stability. Bias stability describes the extent to which the gyroscope output drifts when the sensor is completely stationary. A lower bias instability value indicates better long-term accuracy. This parameter largely determines whether your attitude estimation remains stable. Will pose estimation remain stable, or will it gradually drift over time? This serves as a general reference benchmark. Consumer-grade IMUs may exhibit bias instability as high as tens of degrees per hour. Industrial-grade IMUs typically fall below 10 degrees per hour. Tactical-grade systems can achieve levels below 1 degree per hour. Navigation-grade systems can even reach levels below 0.001 degrees per hour. For professional projects, bias stability should be considered the primary evaluation criterion. The next parameter is angle random walk, typically abbreviated as ARW. ARW reflects the short-term noise characteristics of the gyroscope. While bias stability affects long-term drift, ARW influences the smoothness of short-term data. A lower ARW results in cleaner angular velocity data and smoother attitude estimation. If you are designing a high-performance control system, ARW is crucial. Finally, let's discuss temperature drift. Many sensors perform well in laboratory environments, but their performance degrades significantly in outdoor environments. Temperature drift describes the characteristic of a sensor's zero bias fluctuating with temperature changes. For industrial vehicles, outdoor robots. For marine systems and UAVs, temperature compensation is essential. It is crucial to evaluate performance across the entire temperature range rather at room temperature. Chapter 3, which offers a detailed explanation of accelerometer parameters. We'll begin by discussing accelerometers, which are crucial sensors in many applications. The first important parameter to consider is the acceleration range. Common options for this range typically include values like plus 2g, plus 4g, plus 8g, and plus 16g. For specialized applications such as shock testing, there are even high-range options extending to hundreds of Gs. It's important to remember that, as with many specifications, a larger range isn't always superior. The optimal choice depends on the specific requirements of your application. It is recommended to choose a range approximately 1.5 to 2 times the expected maximum acceleration. The second important parameter is accelerometer bias stability. This affects static tilt measurement accuracy and long-term attitude correction. Typical performance grades include consumer grade 1 to 10 mg, industrial grade 0.1 to 1 mg, tactical grade below 0.1 mg. This parameter is critical for applications requiring precise tilt measurement. Next is velocity random walk (VRW). VRW determines the rate at which velocity errors accumulate when integrating acceleration measurements. If you are developing a navigation system for GNSS-denied environments, autonomous vehicles, or dead reckoning solutions for navigation systems, VRW is a key metric. Another important parameter is noise density. Noise density reflects the inherent noise floor of the sensor. The lower the noise density, the better. This implies that the cleaner the acceleration measurement results, the more stable the positioning performance. The noise density of consumer-grade MEMS sensors typically ranges from 100 to 200 UGHz. Industrial-grade sensors can achieve 20 to 50 UGHz. Tactical-grade sensors can achieve levels below 10 UGHz. Chapter 4. Considerations for magnetometer selection. If you choose a 9-axis IMU, you also need to understand the basics of magnetometers. The primary function of a magnetometer is heading correction. Without heading correction, integration of gyroscope data causes the heading to drift over time. Key factors to consider when selecting a magnetometer include measurement range, resolution, and immunity to magnetic interference are all important considerations. For most applications, measurement range is typically not a limiting factor. Interference is the primary concern. Nearby motors, power lines, steel structures, and magnetic materials can all cause interference. Significant deviations occur in the measurement results. Therefore, the magnetometer requires proper calibration, including hard iron and soft iron compensation. Without calibration, even the best performing magnetometer may provide inaccurate heading information. Chapter 5. Key parameters for engineers to consider. In addition to the performance of the sensor itself, certain system-level specifications are equally important. Sampling rate and output rate determine the data update frequency. Higher rates result in faster responses, but also place greater demands on data processing capabilities. Bandwidth determines the speed at which the sensor responds to motion. Insufficient bandwidth leads to latency. Excessive bandwidth introduces unnecessary vibration noise. The operating temperature range is another key factor. Consumer-grade devices typically have an operating temperature range of only 0 to 60 degrees Celsius. Industrial-grade applications usually require proper operation within a range of 40 to plus 85 degrees Celsius. Finally, the communication interface must also be considered. Common interface options include I2C, SPI UART CAN. SPI is commonly used for high-speed data acquisition. Due to its excellent noise immunity, the CAN bus is widely used in the automotive and industrial sectors. Chapter 6. Industrial Grade. Selecting between tactical grade and navigation grade IMUs. So, how do you choose the right grade of IMU? Industrial grade IMUs are suitable for AGVs, automated guided vehicles, industrial robots, surveying and mapping drones, general automation equipment. Typical gyroscope bias stability ranges from 1 to 10 degrees per hour. Tactical grade IMUs are designed for the following applications: military drones, autonomous driving navigation in GNSS-denied environments, high dynamic platforms, typical gyroscope bias stability ranges from zero point 0.1 to 1 degree per hour. Navigation-grade systems primarily target aircraft, long-endurance UAVs, maritime navigation, underwater systems, missile guidance. These systems typically employ fiber optic gyroscopes and quartz accelerometers with bias stability better than 0.01 degrees per hour. Keep this principle in mind. Always match sensor performance to application requirements. Using an expensive navigation-grade IMU in a low-cost robot is a waste of the budget. Using a low-cost industrial-grade IMU in a precision navigation system is destined to fail. The best IMU is not the most expensive one. It is the one that best meets your performance needs. Select the measurement range based on dynamic motion characteristics. Select bias stability based on accuracy requirements. Select temperature performance based on the operating environment. Select the interface type based on system architecture. Most importantly, focus on bias stability, noise performance, and temperature characteristics rather than just marketing specifications. If you found this guide helpful, please don't forget to like, subscribe, and leave a comment or question below. If you are selecting an IMU for a project, feel free to share your application details and we will help you find the best solution. Thanks for watching and see you in the next video.